So I've made a few videos on my channel about product integrals, geometric integrals, multiplicative integrals, whatever you want to call them, all mean the same thing. And I've mentioned this relationship in the past, in actually the first video I made on this topic. I'll leave a link to that in the description if this is unfamiliar to you. But I never actually really proved it. I stated this, and I'll talk about this in a second, and then I was like, okay, well, this is a discrete relationship, let's make it continuous. And so today I want to correct that and actually prove this statement. So the two things we have to recall are the definition of the additive integral, the Riemann integral. This a lot of people should already know if you're watching this. This is a very similar definition. This is of our product integral here. And so the differences are that this is a sum, this is a product, and that this delta xi is in the exponent instead of being multiplied by f of xi. Now notice how we have a discrete symbol here and a continuous symbol there. So I know it's a little confusing, but there isn't really much better notation. Our third little fact here that we should recall is the discrete relationship between the product and the sum. Okay, we're saying that the product of functions is equal to e to the sum of the natural log of functions. You can see this through examples, and that's kind of just how I developed this idea in the video, in the original video. I should have actually proved this because this is you can do this by induction. I can actually do that in a future video if you guys want. It can kind of actually complete the series. And so what I did then is, and it's very obvious what I did. I was like, okay, well, let's, this is a discrete relationship. Let's just turn it into a continuous relationship where I have pretty much the same thing. It's just all continuous. So this is a discrete product. This is our continuous product, or our product integral. Here we have a discrete sum. Here we have a Riemann integral. But everything else is pretty much the same. We have f of xi, this turns f of x. And then the natural log of f of xi, this is natural log of f of x, right? So pretty much just kind of, turn this into from discrete to continuous, which isn't totally legit because here we're dealing with like integers, or even worse, just natural numbers, and here we're dealing with real numbers. And so, there's a big jump, and I didn't justify what I did because I didn't really know how. I just knew that this worked based on like what I've seen and read and stuff like that. So I knew that the relationship was true, I just didn't know how to get there. Since then, I've actually learned how to actually do this, and it's really not a hard proof, and that's the point of this video, to actually correct what I did. Well, it's not a correction, it's just filling in the gaps. So let's actually prove that. We can begin our proof here. So I'm going to start just over here, and then we're going to end up here, okay, through using these steps and just pretty much, just using these steps, and that's kind of it. The proof isn't really that long. So we're going to start, I'll just start here. So we have the product integral from a to b of f of x to the dx power. This is equal to, well, we know it's equal to this limit, so I'm just going to apply the definition. Okay, so now we have a discrete product here, and we can actually apply this third rule here, this third little relationship. So we have the product equals e to the sum of the natural log of that function, right? So I'm going to keep the limit just stays there, I'm not doing anything to it. And so this product, so notice how here I have just this function. Here the whole function is all of this. I don't actually want to circle it, but it's all of this. This is our entire function. So we have to make sure to bring along the delta xi, okay? Let me just get rid of this now. So we're going to take e to the sum, from I equals 1 to n, of the natural log of this whole thing. So f of xi to the delta xi. Okay, so that's the entire thing there, okay? So now, well, by just log rules, we can move this delta xi to the front. So let me just do that real quick. Okay, so I moved it, you can move it to the front, but I just multiplied it in the back just because that, it's kind of more commonplace to do that. And so here, this should remind you of something. This looks very similar to this. And in fact, this is just the integral of the natural log of the function. So what we have now, well actually, we're almost there. We actually have to do one more step before that, because the entire definition has the limit right in front of the sum. Here we don't have that. We have the limit of e to the sum. However, we can just say e to the limit of the rest of it, because e is a continuous function and we're able to, move the limit inside that function. So let me just copy down the rest of this, and then we can apply this rule here. Okay, so I've applied that, so now what we have is e to the, well actually let me write this a little farther down so it's not so squished. So we have e to the integral from a to b. Just remember that a is equal to x1, and then b is xn, or could be xn minus 1 or something like that, So then this is just the integral of the natural log, so the natural log of f of x dx. And that's it. We actually proved our statement in just a few steps. So we have this equals that, and that's it. So yeah, we actually proved the entire thing in just a few steps, just using a few rules, and that's pretty much the end of the video. So I hope you enjoyed. If you did, then let me know, and yeah, I'll see you in the next video. Bye guys.